We will have 3 papers in this session. Each paper will be 15 minutes for the presentation and 5 minutes for questions. We will do the question answer in Zoom. So if you have a question, then virtually raise your hand. There's a button in the participants tab of Zoom which you probably know. During the talks, I would like to ask you to turn off your video to save bandwidth and to turn off your microphone to not disturb the presentation of the speaker. And with that, we just come to the first of our 3 papers. It's entitled A Unified Approach Towards Computing Warner Diagram, Medial Axis, Delaunay Graph, and Alpha Hull of Planar Closed Curves using Touching Disks. The authors of this paper are Bharat Ram Sundar, Manoj Kumar Mukundan, and Ramanathan Muthuganapati. And Manoj Kumar is giving the presentation. So Manoj Kumar, please.
Hello.
Yeah.
Hello. Sir, can I start?
Yes, we can hear you.
Sir, I am Manoj Kumar. Can I start?
Yes, please go ahead.
Good morning. I am Manoj Kumar, giving a presentation on a unified approach towards converting one-way diagram, medial axis, Delaunay graph, and alpha hull of planar closed curves using touching disk. Now, all these 4 structures are closely related and have a wide range of applications. In these figures, input curves are shown in green color. Delaunay graph and alpha hull are normally computed after converting one-way diagram. Computation of bisectors are involved in converting one-way diagram and medial axis. The 2 inputs, there are 4 bisector segments between these 2 closed curves. Among these, only blue segment contribute to one-way diagram. Only the bisector contributing to one-way diagram is shown here. If few more curves are introduced, the entire portion of this bisector also doesn't become part of the one-way diagram. The unused portion in such case is shown as dashed line. The used portion of bisector can be computed using the portion of curves highlighted in blue color. This local computation of bisector can avoid any further trimming. Input curves are usually approximated by discretizing into points or lines, which makes the computation of bisectors easier. But this creates unmarried edges as shown here. Most of the existing works are based on intersection of bisectors to compute branch points. Aishwar's rectangle has used a piecewise circular approximation of input curves, whereas Leotel has used a spirals to discretize it. But both these works require splitting of multiply connected domains into simply connected ones. In our algorithm, input curves are used as such without any approximation. Branch points are computed without using intersection of bisectors. And moreover, Delaunay graph and alpha hull can be computed without computing one-way diagram. Altogether, a unified algorithmic approach for the computation of the one-way diagram, medial axis, Delaunay graph, and alpha hull has been presented perhaps for the first time. Here input is a set of disjoint planar freeform closed to C1 continuous curves. The case of convex curve are explained first, then modified to include non-convex curves also. It is assumed that input curves are in general position. In all figures, input curves are shown in green color unless specified otherwise. When a disk is tangential to a curve, the point on the curve that just touches the disk is called the put points, and the disk is called the touching disk. The touching disk we discussed do not contain the curves or portion of curves to which it is tangent. So in one-way diagram, touching disks are external to the input curve to which they are tangent.
Excuse me, Manoj Kumar? Could you maybe move a bit closer to the microphone? Like several people in the chat are mentioning that they cannot hear you well and that the volume is quite low. Maybe if you move a bit closer to your microphone, it might improve.
Okay, sir. The microphone is attached to my webcam. I am making it close. Is it audible now?
Now it's better. Yeah, we don't see you, but we hear you better.
Yes, because the microphone is attached to the webcam. So I have to close the webcam.
Okay,
so,
but this now the audio is better.
Okay, sir. Thank you. So a TTD or three-touch disk is a touching disk having 3 foot points. In this figure 3, there are 2 TTDs between curves CA, CB and CC. They are TTD ABC and TTD CBA. Indexing or naming of these TTDs are such that while traversing the boundary of the disk, center is towards the right side. So among the touching disk shown between these 2 curves, the one with the minimum radius is called the minimum antipodal disk, which is highlighted in blue color. They are antipodal because the touching disk foot points are diametrically opposite, and the line connecting these foot points are shown in dashed line. It is called the minimum antipodal line. A touching disk is said to be empty if its interior doesn't intersect with any of the input curves. All disks in the figure are TTDs, among which red disks are empty. Branch disk or BD is an empty TTD whose center is a branch point shown in red color. In order to define a Bernoulli disk, a Bernoulli diagram for 2 closed curves is shown here. It consists of a Bernoulli edge extending to both sides. A Bernoulli disk is a touching disk with the center at the Bernoulli diagram. Radius of Bernoulli disk vary along the Bernoulli edge. It can be expressed as a function called the Bernoulli radius function Ru. And Bernoulli radius function Ru attains local minima at the MADs. A Bernoulli segment is a Bernoulli edge or a portion of a Bernoulli edge. One end of a Bernoulli segment corresponds to Ru of local minima called Rmin, and the other end corresponds to Ru of local maxima called Rmax. Along a Bernoulli segment, Ru varies monotonically between Rmin and Rmax. One of the 2 Bernoulli segments between CA and CB is shown in black color. Other one is shown in blue dashed line extending towards left side. In this figure, instead of MAD, a disk of Rmin is a BD. There exists only one Bernoulli segment in this case. In general, disk of Rmax is always a BD, as shown in figure A and B. But disk of Rmin can be a BD or a MAD. So in figure A, it is a MAD, and in figure B, it is a BD. We mark or identify all Bernoulli segments using directed edges or DEs explained as follows. In the first figure, it can be seen that 2 Bernoulli segments start from the center of an empty MAD. So this MAD AB is the disk of Rmin for 2 Bernoulli segments. Each of the Bernoulli segments can be identified by a directed edge. In the figure, a solid line with a red arrowhead represents a directed edge DEAB between curve CA and CB. DEAB is directed from curve CA to CB. Direction of DE is such that every DE identifies its Bernoulli segment towards its right side. Footpoints of Rmin disk are the endpoints of a DE. DEBA and its Bernoulli segments are shown here. DEBA also use the same footpoints, but direction is from CB to CA. DEAB and DEB are shown together along with their Bernoulli segments. They both coincide as they use the same footpoints, but arrowhead differentiate between these 2 DEs. In this figure, disk of Rmin for this Bernoulli segment is a BD. So footpoints of BD with the curve CA and CB are used to define DEAB. As the center of an empty MAD is the starting point of 2 Bernoulli segments, MADs between all pairs of curves are computed. All MADs are inserted into a list L, sorted in increasing order of radii. Each of these MADs in the list L are processed in the order of their radii. If found empty, DEs are placed using footpoints. For the set of three curves shown here, only MAD AB and MAD BC are empty, and DEs and corresponding one noise segments are shown here. Here, figure in the previous slide has been split into two, showing consecutive DEs. In the first figure, there exists a TTD such that its center is towards the right side of both DEs. One noise segments of these DEs intersect at the center of this TTD. But in the second figure, there is no such TTD towards the right side of consecutive DEs. This way, TTDs towards the right side of consecutive DEs can be used to identify branch disk or BDs. However, number of TTD formation based on consecutive DEs are restricted using parametric closeness of consecutive DEs. For parametric closeness, we can see the second figure where on introducing DE ij, it forms TTDs with the curves which are shown in pink color. So TTD ij are between the curves CI, CJ and CR will not be formed as DE ij and DE JR are not parametrically closest. So parametric closeness ensures formation of at most 4 TTDs on introducing a new DE. So TTDs formed are also inserted into the same list L, keeping the order of radius. All disks, including TTDs in the list L, are processed for emptiness in the order of its appearance in the list. Emptiness of a TTD is decided when its turn in the list L arrives for processing. When the turn of a TTD arrives, it is empty if 2 or all of its 3 DEs are available. So please refer the paper for details. Let us see case 1 where 2 DEs are available when the turn of a TTD ABC arrives for processing. Here DE AB and DE BC of TTD ABC are available. So this TTD ABC is a branch disk as 2 of its DEs are available. As soon as this BD is identified, DE AB and DE BC are deleted so that they will not cause any further TTD formation. One noise segments for DE AB and DE BC are computed, for which TTD ABC is the disk of Rmax. It can be seen in the figure that portion of input curves used for computing one noise segments are highlighted in blue color. One noise segment between CA and CC start from the center of this TTD ABC. TTD ABC is the disk of Rmin for the one noise segment between CA and CC. To mark this one noise segment, DE AC is added using the footpoint of TTD ABC. In case 2, all 3 DEs of TTD ABC are available, so this TTD ABC is a branch disk. So one noise segments are computed and curve portions are highlighted, and DEAB, DEBC and DECA can be seen deleted in here. The correctness of the algorithm is proved through these lemmas. Please refer the paper for details. A working example of the algorithm is explained here with a set of 5 closed curves. MADs between all pairs of these curves are computed and listed in an increasing order of radius as shown here. Here MAD24 is of smallest radius and is empty. So direct edges are added as shown here. So next MAD in the list is MAD12. To verify the emptiness of MAD12, it is enough to check intersection with the curve C4. In general, to verify the emptiness of a MAD, it is enough to check intersection with at most 4 input curves. So for details, please refer the paper for checking the proof in this regard. As MAD12 is found empty, DEs are placed and R12 is deleted. Now TTD421 is formed as its consecutive DEs are available, and radius R421 is added according to its radius. Algorithm proceeds and TTDs are inserted whenever parametrically closest Ds are available. So when the turn of TTD421 arrives, as seen in the second figure, all 3 DEs are available. So this will be identified as a BD, and its one noise segments are computed, and after deleting the corresponding DEs, and highlight portions of curves are so highlighted. So here TTD351 is not empty as its DEs are not available. Whereas TTD324, DE32 and DE24 are available, so it will be identified as a BD, and the one noise segments are computed here for those DEs. And a new DE, DE34 is added to show the Bernoulli segment starting from the center of TTD 324 from here. Now, in this first figure, we can see the DEs are leftover diameter edges, which represents Bernoulli segments extending towards infinity. So, Bernoulli segments corresponding to those DEs can be computed to finish the final Bernoulli diagram. For Bernoulli diagram for non-convex curves, self-bisectors are also involved. Along the self-bisector, touching discs have 2 foot points from the same curve. To avoid this situation, non-convex curves are split at high curvature points. It is a point at the input curve at which curvature is local maximum. Disk associated with the high curvature point is called XCD. An empty XCD acts as the starting point of self-bisector, so its emptiness is also to be checked. For non-convex curves, there are touching disks which are locally maximum, called the maximum antipodal disk. XCD also acts as a disk of Rmax for Bernoulli segment, as shown here. Though center of XCD is not a branch point, it marks the end of a Bernoulli segments, as shown here. Emptiness of XCD is also checked in the case of non-convex curves. Medial axis is the locus of MD maximal disk within the curve. They are computed interior to the curve. The same algorithm for computing Bernoulli diagram can be used to compute medial axis through normal flipping. Advantage of this algorithm is that medial axis of multiply connected domain can be computed without splitting the domain into simply connected one. Delaunay graph is the dual of Bernoulli diagram. Center of two curves are connected by a straight line if they share a Bernoulli segment. Foot point of Rmax and Rmin disk can be used to identify these pair of curves. So the information is listed in the structure H can be used to construct Delaunay graph without constructing Bernoulli diagram. So alpha hull is the union of all Bernoulli disks with radius alpha. A disk of radius alpha will fit only in place where the structure H satisfies this condition. Rmin, alpha is between Rmin and Rmax. So the same structure H can be used to construct alpha hull without constructing Bernoulli diagram. For the implementation, the algorithm is implemented using IRIT geometry kernel. Touching disks are solved using the multivariate constraint solver in IRIT. For their constraint equations, please see reference provided in the paper. Direct edges are implemented using linked list. Freeform curves are represented using NURBS. Curves up to degree 4 have been employed for implementation. Results for Bernoulli diagram for a set of convex curves have been shown here. Figure A to D shows Bernoulli diagram with a leftover diameter edges. Figure A shows branch disk also. Results for Bernoulli diagram for a set of curves including non-convex curves are shown here. In figure B, self-bisectors have been avoided. Results for medial axis are shown here. Figure E shows medial axis computed to a set of closed curves. Figure F shows medial axis for multiply connected domain. Result of Delaunay graph is shown in figure A. Figure B to E show alpha hull for set of curves for different values of alpha. As a comparison, intersection of bisectors are not used in computing branch point. TTD or MAD has a degree of m plus m minus 1, where m is the degree of input curves, whereas bisector is of degree 4m minus 2. No curves containment checks are used for finding empty TTDs as in the case of bisector computation methods. So comparatively lesser intensive computation than other works which use bisector intersection. As input curves are not approximated, computation of branch points are accurate. Algorithms by Lee et al., which works well for simply connected domain, will not work for multiply connected region and a large number of closed curves. And Delaunay graph or alpha hull is computed without computing Bernoulli diagram. None of the previous works deal with all 4 structures in unison for curves. Application to entities with C1 discontinuities has not been considered here. Extension of touching disk to 3 dimension is considered as a future work. To conclude, the developed algorithm has also been demonstrated through implementation. It has been shown that bisector computation is not required to compute the branch point. Branch points are computed accurately as input curves are not approximated. Bernoulli segments are computed using pairs of curve portions identified through touching disk. empty TKDs and thereby BDs are identified without any curve containment check. The algorithm for one-node diagram can handle medial axis with a multiply connected domain. Delaunay graph and AlphaGal can be computed without computing one-node diagram.
Okay, thank you very much for your presentation.
Welcome, sir.
So we are a bit late, but still we have time for a couple of questions. So in the audience, if you have a question, please press the raise hand button that you find somewhere in the participants list. So if you later have some questions, you can post them to the Discord channel. Let me start with one question. So can you say anything about computational complexity? So your method is accurate when it comes to the branch points. Does this come at a price when it comes to computational complexity?
Regarding the computational complexity, the main computation involves in computing all antipodal disks. So there are totally if we complete antipodal minimum antipodal disk between all pairs of curves, there are order of n square computations are there. So there is a major computations involved in this. So the computational accuracy comes around order of n square.
Mm-hmm. Okay. Any other question from the audience? Okay, this does not seem to be the case. Then thank you again for your presentation. And we switch to the second presentation. So if you can please turn off your screen sharing. Oh, I can do that, I think. And then we move on to presentation number 2 in this session. And this is, it's entitled HD-based identification of 3D feature curves and their insertion into 3D meshes. The authors are Chiara Romanengo, Silvia Biasotti, and Bianca Falcidieno. And the talk will be given by Chiara.
Can you hear